Okay, we'll look at some of the homework problems that are in section 12.1. And one of the first problems here is this. Determine whether the conditions PQ is congruent to MN, PR is congruent to MO, and angle Q is congruent to angle N are sufficient to prove that triangle PQR is congruent to triangle MNO, and justify your answer. So the first part of the question is, are those conditions, line segment PQ is congruent to MN, line segment PR is congruent to line segment MO, and line segment and angle Q is congruent to angle N. Okay, what I'm going to do here is draw two triangles here. Here's one, and here's another. All right, the first triangle is going to be P, Q, R. And I'm going to label M and O the same way. Here's M, N on top, and O down here. All right, in this case here, we have PQ, line segment PQ is congruent to line segment MN. So I'm going to mark off those two sides of that triangle. And PR, line segment PR is congruent to line segment MO. Here's PR, and I'm going to mark off MO. And then angle Q is congruent to angle N. Here's angle Q on the top and angle N at the bottom. Now, would this be sufficient enough to prove that triangle PQR is congruent to triangle MNO using one of these properties, either the HL, SAS, or SSS? Okay. Well, we know it's not going to be HL because with the hypotenuse-Leg theorem, we're dealing with right triangles, and these are not right triangles. It's not side angle side because the angle has to be included in between these two sides. And it's not SSS because we know we're not dealing with all sides. We're dealing with two sides and an angle, and two sides and an angle here. So here we cannot, this information would not be sufficient enough to prove that triangle PQR is congruent to triangle MNO. So the answer to that would be no. All right, the next question is justify your answer with the congruence condition and choose the correct answer below. In this case, since we don't have the efficient information to prove that those two triangles are congruent, it would be none of those properties. Okay, so that's problem number one. All right, problem number two is this. Is it possible to find a circle that circumscribes each example of any septagon? And a septagon is the same as the word heptagon, which is a seven-sided figure. If it is possible to find such a circle, choose the correct example of the figure and its circumscribing circle. If it's not possible to find such a circle for every septagon, choose the correct counterexample. Okay. What I'm going to do here is cheat a little bit here, because in the MyMathLab you'll be given this part right here, part A and part B. And of course the septagon means that there are, in this case, 7 sides. And when it's circumscribed, that means that the circle has to be touching all 7 of those vertices. And here in part A, you can see that this particular figure does not have all the vertices touching the circle. So here in this case, this will be A as a counterexample, which means that we cannot circumscribe every septagon. And these, in this case, this one is inscribed in. The circle is on the inside. This one is only 6 sides, and this one is also 6 sides. A septagon is the same as a heptagon, which is a 7-sided figure. Okay? Now, finally, problem number 3. is another situation where you want to find out, is it possible to find a circle that circumscribes each example of a regular octagon? And if it is possible to find such a circle, choose the correct example of the figure and its circumscribing circle. If it is not possible to find such a circle in every regular octagon, choose the correct counterexample. In this case here, an octagon has 7 sides, so that means that in a circumscribed circle, that means that the circle has to be touching all the vertices. And in this case, you can see that C would fit that description, because you have an octagon where the circle is touching all 8 of those vertices. So it is possible to circumscribe every regular octagon.